Hello, Thomson. So maybe I can introduce you first. So Thomson is research. He's a research assistant, research associate at University of Toronto, the Chemical Physics Theory Group, and he's here today to present some work he has done on measurement optimization. So, yeah, is there anything else that you want me to introduce for you, or I can?
Well, yes, PTG group of U of T, and my supervisor is Arthur Ismailov.
Yeah. Nice. Yeah, the floor is yours.
Well, thanks for the introduction. Thanks for having me here. Well, today the talk will be about several methods that try to speed up the measurement process of variational quantum eigensolver. So this qubit picture offers a glimpse of the problem. Usually in a quantum computer, you're measuring the 0 or 1 states of the qubits, and effectively you are measuring the Z operators. But you could rotate your qubits, and if you rotate it this way or that way, you'll be able to measure the X or Y operator. So you can imagine that when you have multiple qubits, things could get complicated. So in the next few slides, I want to make the complexity of the problem concrete. So the outline of the talk is as follows. I'm sure you're all familiar with variational quantum eigensolver, so I'll just quickly go through the basics. And in the VQE particularly, I want to focus on the measurement parts of VQE. I want to state the problem there and what we are trying to achieve with measurement optimization. And then there'll be several methods in the qubit or fermionic space that speed up the measurements in VQE. And I'll show you some results and conclude the talk. So initially, and still to this day, VQE is used to solve quantum chemistry problem, where usually you have a molecules, and in this case, it's H2O, and you want to understand its properties, how it interacts with the world. Well, because the nuclei is generally heavier than the electrons in the molecule, you just want to focus on the electronic degrees of freedom in your molecule. So what you do is you write down the Hamiltonian of the electronic degrees of freedom, and you want to solve for its eigenstates. And of all the eigenstates, you're generally interested in the ground state and the ground state energy. So that's denoted by subscript 0. For the purpose of this talk, we'll have like 2 ways of writing down the Hamiltonian. One is the fermionic, and the other is qubits. So the fermionic picture uses this representation that you may have saw from H2 as an example for quantum mechanics. So what you do is you figure out some orbitals where you could put your electrons. And in the case of molecule, we chose n orbitals that your electrons could occupy. And what you then do is you compute these HPQ and GPQRS coefficients that represent the energy you would have if you were to have certain electrons occupying some orbitals. So after we have written down the fermionic Hamiltonian from physics, you can do something called Jordan-Wigner transformation or Brovik-Katav, and that will allow you to go to the qubit representation. And the qubit representation, instead of creation and annihilation operator, you have these pk operators, and they are just tensor products of XYZ operators. So the number of these Pauli operators, let's denote it n. We know that n will scales with n to the 4, where n is the number of orbitals you chose to represent your Hamiltonian n. And we know that because you could look at the GPQRS term, and all 4 indices goes up from 1 to n, so you would at most have n to 4 terms. So after you have written down the Hamiltonian, you want to solve for its ground states. And the variational quantum eigensolver does that by using the variational principle. So you minimize with respect to theta, you parameterize a wave function, and you at the end you would get the ground state energy. So of course you do this on the quantum computer, you prepare the wave function, and you get the energy, you feed this to a classical optimizer. So as I said before, we're focusing on the measurement parts of the VQE. And it's not as simple as preparing a wave function and you directly get the energy expectation value. So just to show why it isn't that simple, let's look at an example of the Hamiltonian. And here, Hamiltonian usually is a sum over these polywords. And let's say these are the first two terms of your Hamiltonian. So you have two problems. And the first is your quantum computer measuring the 0 or 1 states only allow you to directly get the expectation value of Z. So it's actually easier to measure this term, and let's focus on that. The second problem is if you want to measure Z1, Z2, what do? You look at qubit 1, you look at qubit 2, you get the result, and you multiply the results, you get a number called, let's call SZZ. And this is a sample of the your Z1, Z2 value, and this would turn out to be either plus or minus 1. The problem here is that SZZ is not actually the expectation value of your Z1, Z2 operator, simply because your wave function psi theta isn't an eigenstate of Z1, Z2. So by measuring the Z1, Z2 operator, you have to collapse your wave function. And you actually have to prepare your psi theta again. So you go back here, you prepare this all again, and then you get another sample. And the way you get your expectation value is by defining this estimator for the for Z1, Z2. And what you do, you average over a bunch of samples. So say you obtain K samples, you average over them, and that's your estimate of the expectation value. So that was the first term. And we said second term, that first term was easier, second term, but the second term wasn't as hard. And this is like the first slide that you saw. What you have to do to measure the second term, you want to rotate your measurement basis into the bases that allow you to measure the X1. So you can show that with this simple unitary, this is just acting on the first qubits, you can rotate into a basis where your X1 operator becomes Z1. And what you do on VQE then is you start with the psi wave function that VQE gives you. You rotate it into the measurement basis that you want, and then you just need to measure a bunch of Z operators, which we know how to do. So I think this is like this is the first algorithm proposed to measure the expectation value of your Hamiltonian, is to look at all of the terms, all of the poly operators that you have in your Hamiltonian and measure them one by one. And we said earlier that the total number of these poly operators scales with n to the 4. So at least you need n to the 4 repetitions of preparing the wave function psi and measuring on a quantum computer. And that is very inefficient. So here's an example of how inefficient that is. The Google team, who are also studying this problem, look at some water molecules or hydrogen chain. And you can see these number of qubits being 12, 16, or 14. Like these are the size of problems that you could really solve on your classical computers. But if you were to use VQE and use the most naive measurement scheme that we talked about earlier. So on this graph, they would be the green circles. That would need like 10 to the 9 circuit repetition. So 10 to the 9 here, 10 to the 9 here, and just to get one expectation value of the Hamiltonian. And that's not enough for the variational quantum eigensolver, because after you obtain the expectation value, you want to feed this number into your classical optimizer, and your optimizer will go back, change your theta, and for each unique theta, you need to do this all again. So we really want to figure out a good way of reducing the cost of measurements. And we could look at the ideal case of a measurement and ask the question of what if you could measure the entire Hamiltonian at once? What would it look like? So again, the Hamiltonian is just a sum over these Pauli operators, and they are tensor products of sigma, and sigma being XYZ operator or identity. If you want to measure your entire Hamiltonian at once, you would have to find the Hamiltonian in this form. So you have unitaries on the outside, and you have Z operators that you could measure on the inside. So you have to do two things, really. You want to identify the unitaries operator and apply this classically, UHU dagger, on a classical computer, because you want to compute the function of Z operator, and that will tell you what kind of operators you want to measure on a quantum computer. The second thing you want to do is you want to apply this unitary on the wave function that BQE prepares. And you could verify this equality by resolution of identities that getting the expectation value of Hamiltonian is exactly equal to getting expectation value of the function Z operator in this rotated basis. So on the VQE, you're just introducing an extra unitary, and then you measure this function Z operator. Now, this is the ideal case, and we could see immediately why this isn't possible by looking at the matrix representation of these Z operators. So these Z operators, if you do the tensor products, you would end up with a diagonal matrix with 2 to the n dimension. So you realize that actually finding this unitary is equivalent to solving the eigenvalue problem of your Hamiltonian. And of course, that's not possible. So what we do in practice is we use the fact that the expectation value is linear. So instead of measuring this entire Hamiltonian, we could express the Hamiltonian as a sum over these simpler fragments. And these fragments, you want them to be simple in the sense that you could figure out what kind of unitaries you need to rotate them in the basis that they're all just Z operators. And these Z operators you can measure on VQE. And then instead of measuring the expectation value immediately, you measure the individual expectation value, and you do this for n times. So that poses the goal for us that we generally want to decrease the number n, and that would translate into lower repetitions on VQE. And the exact way we go about that is twofold. So you want to define what type of operators, HM, that you could measure. And for these type of operators, you will be able to figure out what kind of unitary you want to apply on a computer and what kind of function Z operator you will measure at the end. The second thing you want to figure out is that once you've defined the form of HM, you still need to figure out, given the Hamiltonian, how do you separate it into a linear combination of measurable parts. So to show you that, let's look at the simplest example I know, and that is the Keyboardwise commuting method. So as the name suggests, the Keyboardwise commuting methods require all of the terms in your measurable group HM to commute qubitwise. So here's the example. You have two terms here only, and these two terms commute qubitwise because on individual qubits, they all have the same Pauli matrices. So on the first qubit, it's X here as well. And the second qubit is all Y. And on the third qubit, it's Z or identity, and that's fine. So whenever you have a fragment that has these type of terms that commute qubitwise, you could easily imagine that on the first qubits, all you have to do is to figure out the single qubit unitary that diagonalize your X matrices. And this is just a 2x2 matrices. You can easily figure out what that is. And you do the same for the Y2 operator, and you get U1 and U2 on the first and second qubits. And the total unitaries you need then would be the product of U1, U2. And when you apply it onto these two operators, you find that both of them just become Z1, Z2 operators. So this is a nice method in the sense that the unitary is very simple. So remember, the unitaries you have to put on the variational quantum eigensolver, and that would add on to the cost of the circuits. So these are, you only need single qubit unitaries for Keyboardwise commuting groups. So at most, it scales with O(n), where n is the number of qubits or number of orbitals. The downside of Keyboardwise commuting is that the commute Keyboardwise condition is very strict. So most of the time, the terms don't have exactly the same Pauli matrices on all qubits. So empirically, what we found is generally the number of terms in the same group, if you pursue this method, would be like 2 to 3. So this only offers like a constant speed up over the most naive approach of measuring individual qubits. So one way to improve on this method is to relax the condition, because commuting qubitwise is too hard. And instead, we can say that we can measure all of the commuting terms. So that's the fully commuting method. And here's another example that shows the differences. So say you have X, Y, and Z terms. And these operators obviously don't qubitwise commute, because on both the first and the second qubits, they all have different Pauli matrices, it's X, Y, Z. But what you can do, you can show that these three Pauli operators, they mutually commute. So what this will allow you to do is easily find the unitaries that will rotate all of them into just Z operators. And these unitaries we know are Clifford gates, and there's a known decomposition that quite efficiently implement them on quantum computer. I skipped all the details of creating this unitary, and I just want to say a few things about this. Essentially, the trick is whenever you have a set of commuting polywords. So first of all, you can represent polywords in a binary vector space. And then if all of your polywords commute, you can find a basis in the binary vector space. And these spaces will have the nice property that they also mutually commute. And when that's the case, that's the property you need to locate the unitaries that diagonalize all of the operator at once. So I found the trick really neat. I don't have the time to go into the details, but if you're interested, this is covered in the paper below. So far in Keyboardwise Commuting and fully commuting method, we talk about the form of the measurable group, and we require all of them to commute in a sense, commute Keyboardwise or just commuting with all the terms within the fragments. We haven't covered is whenever we're given a Hamiltonian, how do we actually write it as a sum of these measurable groups? So we notice that the central relations that we care about here, it's a binary relation, whether two polywords commute or Keyboardwise commutes. It's a binary relation. So what you can actually do is you could represent this on a graph. Let's say you have this Hamiltonian and you have only 6 terms. You could represent the poly operators as vertices. So you have Z1, Z2 as the vertices here, and Z1, Z2, Z3 as another vertices. So these two, we know that they commute. And to represent that, we have an edge between these two vertices. You could do this for Keyboardwise commuting as well, just changing the condition for the existence of an edge. And you can represent the commutation relations between all of the polywords within your Hamiltonian. So once you have that, the way to group the terms in your Hamiltonian into fully commuting fragments, HM, is as follows. So we use the same graph, and what we really want to find are these fully connected subgraphs. And because the edges represent commutation, the fully connected subgraphs says all of these polywords commutes or Keyboardwise commutes. And this is what in the graph theory called cliques. The second problem, the second part of the puzzle is you want these cliques to cover all of the edges, because you want to measure the expectation value of the Hamiltonian. You don't want to miss polywords or two. And that's the cover part of your problem. So combine, this is called the clique covering problem. And the third part, the minimum part, says that usually when you're given a graph like this with 6 edges, there's a lot of different choices of clique covering. So here there are 2 examples. One is having these 2 triangles. They're both cliques and they cover all the vertices. And the second choice is to have just 2 polywords grouped together, and that's another choice of clique covering. So the intuition that we use here is generally the number of groups or the number of cliques in this case correlates with how many repetitions you need to do on a Variational Quantum Eigensolver. So you really want to find the choice of clique covering that has the least number of cliques. So in these 2 examples, you would prefer this one because you only have 2 cliques. And on the right-hand side, we have some results in terms of number of groups. So on the x-axis, these are just the number of terms in your Hamiltonian. On the y-axis, it's the number of groups. We'll call it n. And we have 3 lines here. The blue line, total, is just the most naive approach. So you're measuring individual polywords one by one. And on this plot, this is like the x equal to y plot. In some sense, you can think of it as the original difficulty of the measurement problem. And then you try Keyboardwise commuting and fully commuting. So as I said before, the Keyboardwise commuting terms method usually has like 2 or 3 polywords in the same group. So that offers like a constant speed up over the most naive one, and it doesn't change the scaling. So both of them are scales with n to the 4 in terms of number of groups. But fully commuting, because now we have relaxed the condition, you can actually show both empirically and theoretically that there is a clique covering that only has n to the 3 scaling with number of orbitals. So here are the results for the measurement schemes in the qubit space. But there's still a way to improve on this scaling in M. And to do that, we need to look at the fermionic algebra. So here, for reference, I include the form of decomposition in the qubit space. You have unitaries on either side, and you have Z operator at the center, which is something you could measure. So we want to do the same thing in the fermionic algebra. And the way we do that is to do it by analog. What do we choose as unitaries here, and what is equal to Z operators? So our choice would be using the orbital rotations as your unitary. And this is because the orbital rotations has a really nice property that you can almost think of it as a n by n matrix, unitary matrix that rotates these creation operator as a basis, as a vector. So if you rotate it with a unitary operator, you can write it as a UPQ and AQ. So we know what unitaries we want to use. What's the equivalent of Z operators? In the fermionic algebra, that would be the number operator. And these are creation and annihilation operator onto the same indices. If you do the Jordan-Wigner transformation, you can see that the Z operators and the number operators are the same up to a constant. So both of these things you can measure on a quantum computer. So putting all of the puzzles together, we have the following decomposition for Hamiltonian. You have just number operator at the center, and on the outside, you have orbital rotations. And you could write them in terms of the creation and annihilation operator. So this defines the type of decomposition we want to have. We still need to figure out how do we do a decomposition given the Hamiltonian. So I'll start by introducing an approach developed by the Google and Berkeley team. And the way they do this is we notice that there are two separate terms in the Hamiltonian. This is usually called the one-body term, and this is called the two-body terms. And it turns out that the one-body term, you can measure all of these things in just a single measurement. And the way you can see this is you take the HPQ as a matrix, where P and Q goes from 1 to n. And this is a matrix that happens to be Hermitian. And this comes from the fact that there's a physical system behind this fermionic Hamiltonian. And given a Hermitian matrix HPQ, you can actually diagonalize it. So you can find a decomposition in this form. And here we can use the nice equivalence between the unitary matrix and the unitary and the orbital rotations. So once we diagonalize, find the unitaries matrix that diagonalize HPQ, we can find the corresponding unitary operator, U. And if we apply it onto the Hamiltonian, onto the one-body terms, we will find just a sum over the number operators at the center. So just to remind you, this unitary you can put on a wave function, and then you can measure the entirety of one-body term just by looking at the sample of the number operator. So that dealt with the one-body term, and that'll leave us with the two-body terms. So in the following slides, I'll refer to the Google's and Berkeley's methods as a singular value decomposition, and you'll see why in how we decompose the two-body terms. So the first thing we do is GPQRS is a 4-mode tensor, but you could think of it as a matrix if you group the PQ indices and if you group the RS indices into one. So instead of a n by n by n by n tensor, you now have a n square by n square matrix representing G. What you can then do is, again, just diagonalize it, do a SVD, and you distribute the eigenvalue onto the onto both of the vectors that you have. And these are vector because PQs are composite indices. So once you have this decomposition of the tensor, you can plug this back into your two-body terms and arrive at this first equation. And nice thing about this is that here you see the one-body term. And we saw earlier how we dealt with the one-body term just by diagonalizing the LPQ matrix. You could do the same here. Once you diagonalize it, expand the square, you get instead this equation. So let's check the form if it's what we expected. On either side, we have unitaries, and still we just have number operator at the center. So that's what we want. And the nice thing about this method is that because we're using SVD, we know for sure that the number of groups M scales with the square, scales with the n square. And that's because the GPQRS tensor has like n squared by n square size. And when you diagonalize it, you get at most like n square eigenvalues and eigenvectors. So if you compare this to the qubit methods, the best was fully commuting is n cubed. So now you have further reduced the scaling with respect to n. But there's still ways to improve on this. And this is what we call the Cartan subalgebra approach. And Cartan subalgebra is really just referring to the number operators here. We call it that because potentially you could write your Hamiltonian in other algebra. But in Fermionic Algebra, really we're going for what we said before, just unitaries and number operator at centers. So the difference between Cartan subalgebra and the SVD approach is in how we partition the Hamiltonian. So we chose to deal with the one-body term the same way they did. It's a nice trick that measures all of the one-body term at once. And the difference lies in how we deal with the two-body terms. So here I wrote down, again, the decomposition of the two-body terms using the SVD method or the CSA method. And everything else is the same. You notice that it's the same unitaries and the same number operator, and the difference is in the coefficients. So to draw a parallel, you could consider VTVU coefficients, so these two, as a n by n matrix, VTU. And when you compare that to the CSA decomposition with lambda, you notice that V isn't as general as lambda. And that's because V come from an outer product of two vectors, VTVU. So if you do, this is a rank 1 matrix, really. Whereas if you look at lambda, this could be 4 rank. This could be anything. So in a sense, the CSA decomposition has a more general form of the measurable group compared to the SVD method. And that's why you'd expect that in terms of the number of groups, your MCSA would be lower than MSVD. And we know numerically that MCSA scales with roughly n to the 1.4, somewhat better than the SVD method. Now, the problem of CSA method is now the SVD trick doesn't work. So SVD tells you deterministically what kind of coefficients VTV you are and what kind of unitaries you need to use. But now when you're going for the CSA decomposition, you no longer have a known solution. So you have to resort to a nonlinear optimization where you vary lambda and unitaries. So a little bit more about the nonlinear decomposition. On the left-hand side, this is the two-body term we try to decompose. And on the right-hand side, this is what you saw before with number operator expanded. So an L expanded into creation and annihilation operator. You could apply the unitary operator onto the ALAK and show that in terms of tensor, what you want to do is this sort of decomposition. And in some sense, you can see it almost like a diagonalization for a tensor. And the diagonalization is in the sense that your diagonal tensor now has only two non-zero dimensions, two non-zero modes. And your unitaries, because you have four indices, it's applied twice to your tensor. So tensor decomposition, we look into whether other people have studied the problem, but we found nothing that solves this directly in terms of the optimal, the lowest number of M you need. So what we resort to is the BFGS optimization. So we use the lambda as a parameter, and we parameterize the unitary, and we try to make this equality works. So far, we saw a bunch of different methods, and they all decrease the scaling of M with respect to the number of orbitals. And before showing you the results in terms of number of groups, I want to question that whether M is a good metric for comparing different methods. And to see, so it's not. And to see why it's not, we need to look at how we estimate the expectation value of your Hamiltonian. So say you decompose your Hamiltonian into these parts, and you define the estimator of the expectation value. The estimator of the energy expectation value is just the sum over the estimator for individual fragments, because measurement is linear. And the individual fragments is something you could sample directly. So you average over, say, we spend km measurements onto the m fragments, then this would be the equation. You're just averaging over your samples. What we really want instead of m is we want to get to the expectation value of the Hamiltonian as quickly as possible. So the thing that we care about should be the variance of your estimator. And we could look at what it should be. And the first equality, it comes from the fact that the individual fragments are measured independently using a different wave function, using a separately prepared wave function. So their variances of the EH would simply be the sum of variances of the fragments. So the variance of the individual estimator, you could figure out this to be 1/k times the variance that came from quantum mechanics. So if you look at the variance of your sample, this would give you the quantum mechanics variances of your HM operator. And 1/k factor comes from the fact that when you take the variance of this factor, it gives you 1/k squared, and you're summing over a bunch of samples that all have variances of HM. So we found this metric that we care about, but there is degrees of freedom here, and that is the number kn. So kn is the number of measurements you spent, is the number of measurement you spent on measuring the nth fragments. And there's a freedom in allocating how many measurements you spent on multiple fragments you have. So actually, there's a way to figure out the optimal choice of the measurement allocation, and we'll look at that here. So the goal is you want to minimize the sum over the total number of measurements you spent, and you have a constraint on how far off your expectation value can be from the estimator of your EH. So that translates to having a constraint of variance of your estimator. So you have something to minimize and you have a constraint. This is something you can use the Lagrange multiplier for. And once you solve the Lagrange multiplier by taking derivative with respect to Km, you will arrive at the minimum value of K and to be this function of the variances of the fragments. So M really is a proxy for how big K is. And we'll see why that affects things. So here are the results. On the rows of these tables, we have several molecules, simple molecules that we could compute. And on the columns are methods that we covered earlier. So in order, we have the most naive approach that measure individual polyworks and Keyboardwise commuting, fully commuting up until GCSA. As we claim before, as you increase in the complexity of the measurement scheme, you are steadily decreasing the number of groups you need to measure the Hamiltonian. So from here to here, you see a decrease in the number of groups. What's interesting is when we look at the number of measurements you need, so the equation that cares about the variance of the fragments, we saw the first three columns are, as expected, decrease from the most naive one to fully commuting. But when we look at the Fermionic Algebra method, it turns out that even though your number of groups is decreasing as you go from here to here, your number of variances is actually increasing. Your number of measurements you need is actually increasing because of the variances of the fragments aren't favorable. So this is where we change the direction of the research and try to instead account for K. And K is proportional up to a constant to this expression involving the variance of the fragments. And there are two ways that we thought of to account for this number. And one is, remember in the CSA decomposition, we were doing a optimization. What you can do is in the optimization, you add the variance terms into the cost function. And that will force your optimizer to also care about this K, symmetric K. And the second heuristics is you want to exploit the property of the square root function. So this is a sum over square roots of the variances. And the way you reduce this kind of equation is generally you want to have an uneven distribution of variances of the term. So for example, you want to have the variances of the first two terms or the first few terms to be a lot larger than the rest of the fragments. And to show why is that intuition, let's consider example with two fragments. So say you have a choice between having a variances of 4 on two fragments or just having a variance of 8 on one of the two fragments. They all sum up to 8, but which one would you prefer when you plug these two numbers into the equation for K? if you work out the math, you would find that the first fragment turns out to be 16, and the second one turns out to be 8. And the intuition for that is whenever you take the square root, and when you take the square root of that onto the number 8, it gets rid of a lot more variances than you would if you take the square root on 4 individually. So these two are the heuristics, and we could apply that onto the CSA decomposition. And the first heuristics, let's call it VCSA, is simply adding the penalty term. So you could write the original CSA in this minimization. And instead of minimizing that cost function, we now add an extra term that is proportional to k, number of measurements you need. And here, the alpha is a term that balances the importance between the first term and the second term. The first term is necessary because you want to express your Hamiltonian in linear combination of Hn. And the second term is also important because that's the number of measurements you need. So in practice, we found choosing alpha to be 10 to the -5 works. We want the first term to be almost 0, but we also want the optimizer to care about the second term. So one problem that I didn't mention is that in principle, you can't actually compute these variances of the HM. And that is because in the Variational Quantum Eigensolver, you are preparing a wave function psi that you don't know how to write down classically. So if you don't know how to write down psi classically, you can't compute the variances of these HM. But what you can do is usually in quantum chemistry, we have a fairly good starting point. And in this case, we're using Hartree-Fock wave function most of the time. And these Hartree-Fock wave functions has a sufficient overlap with the ground states. And whenever that's the case, you can assume that within the cycles of VQE, you'll mostly prepare a wave function psi that are close to the Hartree-Fock wave function as well. So you could classically approximate these variances terms using a Hartree-Fock wave function. And the good thing about that is it's fairly easy to compute those wave functions. So that was the first heuristics. The second heuristics brings us to the GCSA method. And here we're going for the uneven distribution of variances. So hopefully using the example earlier, I convinced you that this uneven distribution generally leads to lower sum over square roots. So the way we achieve this uneven distribution variance is by having an uneven distribution in the norm of the fragments. So compared to the original CSA decomposition, where you optimize all of the fragments at once, you can actually do this step by step. So you say the first term you want to measure H1, you want most of the coefficients of the Hamiltonian to go to H1. So you do this first, and after you have done the minimization, at the case step, so at the small case step, you fix the previous choices of the HM that you converge to, and you just focus on minimizing the current fragments. And you do this until converging, until all of your fragments sum up to the Hamiltonian. So you can imagine that at the first step, because you're only minimizing a single fragment, most of the coefficient go to the first term, and compared to the case step later, your H1 will have generally higher norm and coefficients and higher variances because of that. So these are the two modifications we did to CSA. And finally, I can show you the results of these methods. And again, we have the number of groups as a first table. And on these columns, there's a new methods that I didn't introduce, but essentially it's the fully commuting method, but using the uneven distribution heuristics. So you could apply the same thing to fully commuting group, and you will obtain a better methods as well. So in terms of number of groups, we see that this is what we expected. The number of fully commuting groups is scales a lot faster than all of the Fermionic Algebra methods. But when we look at the number of measurements, so in the last three columns, compared to SVD, our improvements based on the heuristics actually give us results that are better than SVD now. But if we look at the GFC method, we actually found that the fully commuting method is still the best compared to all others. So we've gone full circle. We started with improving fully commuting and found out it was still the best. Well, that might be true, but there's one hidden concern for fully commuting method, is that the number of groups, as we show, as well, I told you that fully commuting scales n to the 3. So that's a lot higher than the fermionic method. And potentially, as we look at bigger and bigger molecules, as n grows, the number of groups might finally catch up to the number of measurements that fully commuting needs. So it's still something to investigate in the future, how scaling affects these methods. So in conclusion, the measurement parts of variational quantum eigensolver could be very costly. And this is the example that you saw earlier. Something 12 qubits you could solve on your classical computer takes like 10 to the 9 repetitions to just get go through a single loop of variational method. So you really want to figure out a efficient partitioning where you have your Hamiltonian as a sum of measurable groups. And if you do that well, we see it in this graph that compared to the naive green circles, you can have something almost 100 times or more better methods. The second thing we learned is you could consider M when you're developing your method. So M is the number of groups, but really it's a proxy for the number of measurements, K. And there are some heuristics like considering approximating the variances, or you could go for an uneven distribution in variances, and these would greatly reduce the final cost of your method. So that's it from me, and thanks for your attention.
Hey, thanks, Thomson. That was a very pedagogical and easy to follow presentation. Yeah, thanks a lot.
Thank you.
Do you want to take questions? I guess.
Yeah, of course. I mean, I'm surprised that there's no question during the presentation, but yeah, ask away.
Oh, okay. So for me, I have something I want to clarify. So when you do the optimizations in the Fermionic algebra, after you find the unitaries, in the end, you still have to do the mapping to the qubit space, right? To actually measure the expectation values on the quantum computer.
Yes, you're right. So you might be wondering how difficult that is. And this is actually something covered by the Google and Berkeley team in this paper. That's the orbital rotations, unitaries, are fairly efficient on quantum computer. I think it's like a square scaling where n is the number of qubits. So there's a known exact decomposition that doesn't require any trotterization.
Oh wow, thank you, thank you. Yeah. Any questions from the rest of the audience? If not, then I have another question. So far for the results that you showed, the GFC, which is the fully commuting but variance ordered. So what do you mean by variance ordered in the fully commuting case? Because you're exactly partitioning it via the minimum click cover problem, right? So so when you mean variance ordered, you mean you minimize according to one fragment first, or what?
So if I understand you correctly, you're asking how do you do the GFC decomposition, right?
Yeah.
Yeah, I see. Right. So if you were to do GFC, you don't actually go for the minimum click cover problem. So this minimum click cover was entirely inspired by reducing the number of groups. But now if you want to do GFC, which wants to have an uneven distribution of variances, you want to look at the coefficients of your polywords, because in your Hamiltonian, usually there are several terms that has a lot larger coefficients than other terms. So there is an order of importance between these polywords. Then what you can do is, this is something proposed by the Crawford groups doing GFC. And what they do is they order the polywords in terms of the size of the coefficient. And if you group the polywords with a bigger coefficient first, then you'll generally end up with the first few groups having higher variances than the rest. And that's essentially how you go about GFC. So no click covering.
I see. Which is the paper that explains the GFC method?
Sorry?
Where can you find a GFC method in the literature?
Right. So this is, I should emphasize this during the presentation, but it's okay. So this is done by Crawford and Stephen Berkeley, and they published in Quantum. Here's the archive.
Nice. Thank you. Oh, one more question from me is, so in our current era where, cloud, for example, IBM, you can only make a maximum of 8192 shots per iteration. So since there's a limitation to the number of shots you can make on the quantum computer for each step of the VQE, will you say that the GFC method is the best because there's a limit to how many shots you can make? So if the number of shots is too little, the variance will be too high. So based on the variance measurement, seems like the GFC method is the best. I don't know. I'm just thinking out loud here.
Yeah. So you're right. So variance is generally how you. So in this case, the K is how you compare it between different methods. And based on the table here, GFC has the best variances. It's just that we don't know how much this would scale as you go for larger and larger molecules. But for hardware that we have today, yes, I think GFC is the best.
In the future, where let's say it is easier to, in the future where let's say you can make a lot of shots on the same wave function once it is prepared. For example, let's say you can make 1 million shots on the same wave function, but it is hard to prepare another wave function. So in that framework, it is the other methods will be better, right? Because we can more easily reduce the variance because measurements on the same group is cheap if we can make a lot of shots on the same wave function.
Okay, so if we're So if we fix the number of shots available to us, and we're still looking at these fairly small size molecules on this table, then it doesn't really matter how many number of shots you have. If you look at this number of measurement k, this tells you how much one method is better than the other. So the way number of shots could affect things is that it allows you to look at bigger molecules. So when you go for bigger molecules, they have a different scale. Different methods have different scalings as n grows larger. So the problem of GFC is that so for now we're looking at smaller molecules and it has lower k, but when we go for larger n, we expect the number of groups for GFC to skyrocket faster than the other methods. And it's possible that this would eventually affect the number of measurements for GFC. So if we have more shots available and look at, more importantly, look at the bigger molecules, then it's possible that the CSA methods and SVD methods would be superior in those regimes.
I see. Thanks, Thomson.
It's something to investigate in the future. Not something to have now.
Any questions from the rest? If not, then yeah, Thomson, thank you for your time. It's pretty early at where you're at now, right? So thanks for taking the time to speak to us so early.
Thanks for being here at was it 9 p.m. at night?
Yeah, it's 9 p.m. outside.
Okay, thank you very much.
Yeah,
and good night, everyone.